Alright guys, so today we are going to learn how to do stoichiometry with gas volumes. Very easy conversion. Then we're going to learn how to use density as a conversion factor, and then we're going to learn how to calculate percent yield. Now, calculating with the volume of a gas. If you have a substance that is a gas and you need to go to volume, we can use the molar volume conversion. So the molar volume is 1 mole of gas is equal to 22.4 liters. Now this happens at STP conditions. So STP stands for standard temperature and pressure. The standard temperature is 0 degrees Celsius. The pressure is 1 atm. If conditions are not at STP, we cannot use this conversion, but we'll learn about that later. Now think about how big 22.4 liters is. So think of a 2-liter bottle of soda. If you have about 11 liters of 11 bottles of the bottles of soda, then you have a little under 1 mole of gas. So this should kind of give you an idea of how much space gases actually take up, okay? Now, if you have a liquid, you cannot use the 22.4 conversion. You can only use that when you're talking about gases. So let's look at this example. It says, how many liters of hydrogen gas at STP could theoretically be produced by reacting 3.400 grams of sodium with excess water? So first we need to write our balanced equation. So we have sodium, which is a solid, reacting with water. Now remember, you can write water as HOH. That helps the balancing. That is a liquid. And that is going to produce sodium hydroxide, which is aqueous, and hydrogen gas. Okay. Now we need to balance these. So when I balance, I'm going to need to put a 2 in front of the water, a 2 in front of the sodium hydroxide, and a 2 in front of the sodium. Okay, so that is our balanced equation. Now remember, there's an understood 1 in front of the hydrogen. Now our next step is to write our map, our conversion map. So first let's start with our given. Okay, we are given 3.400 grams of sodium. Okay, that's our given. And we need, it is asking for liters of hydrogen gas. Okay, so we're starting with 3.400 grams of sodium, and we need liters of hydrogen gas. So our first conversion, we're going to go from 3.400 grams of sodium to moles of sodium using the molar mass of sodium. Then we're going to go from moles of sodium to moles of hydrogen using that molar conversion. So there are 2 moles of sodium for every 1 mole of hydrogen. That mole-to-mole ratio comes from our balanced equation, so it's our coefficients from our balanced equation. Then we're going to go from moles of hydrogen to liters of hydrogen. Okay, this is when we're going to use our 22.4. So there's 22.4 liters in 1 mole. It doesn't matter what kind of gas you're talking about. It could be hydrogen, it could be nitrogen, it could be carbon dioxide, but the conversion is going to be the same. It's going to be 22.4 liters. All right, so now we're going to set up our conversion. Now we're doing 3 conversions, so we're drawing 3 lines. Okay? Start with your given, 3.400 grams of sodium. So since we have grams of sodium on top, we're going to have grams of sodium on the bottom. And we're going to use the molar mass of sodium. Now remember, molar mass comes from your periodic table. So sodium's molar mass is 22.99 grams of sodium. On the bottom, 1 mole of sodium is going to go on top. So we went from grams of sodium to moles of sodium. Now we're going to go from moles of sodium to moles of hydrogen using our molar ratio. So we're going to have 2 moles of sodium on the bottom and 1 mole of hydrogen on top. So that gets us from moles of sodium to moles of hydrogen. Now we are going to go from moles of hydrogen to liters of hydrogen using 22.4. So we're going to put 1 mole of hydrogen on the bottom, again because our unit on top is H2, and then we're going to have 22.4 liters of hydrogen on top. Okay, so now we are going to calculate this. So we are going to multiply across the top. So we're going to do 3.4. Let me push this up. Okay, so we'll do 3.4 times 22.4. So that gives me 76.16 on top. Okay, and then we're going to do 22.99 times 2, so that gives me 45.98 on the bottom. And then we're going to divide 76.16 divided by 45.98, and that is going to give me, now we have 4 sig figs, so that's going to give me 1.656 liters of H2. Okay, 1.656 liters of H2. Now that makes sense because look at how little sodium we have. We got a little sodium compared to how many grams are in a mole. So it makes sense that we have a little liters compared to how many liters are in a mole. Okay. And also it's a 2-to-1 ratio of 2 sodiums to 1 hydrogen. Okay. Now let's look at our next example. It says if we have 5.33 times 10 to the 23rd molecules of hydrogen gas react with excess chlorine gas, how many liters of hydrogen chloride gas could potentially be formed at STP? So this is a synthesis reaction. We got hydrogen gas reacting with chlorine gas, and it's forming hydrogen chloride gas. So to balance, you're just going to put a 2 in front of the HCl, and there will be 1. So now you may see HCl and think, isn't that hydrochloric acid? But remember, acids are not acids unless they are dissolved in water. So in this case, we don't have an acid. We just have a hydrogen chloride. Okay? So now start with your given. We are given 5.33 times 10 to the 23rd molecules of hydrogen gas, and we need liters of hydrogen chloride gas. Okay, so let's start our map. So 5.33 times 10 to the 23rd molecules of hydrogen gas. We're to convert that to moles of hydrogen gas using Avogadro's number. So 6.022 times 10 to the 23rd equals 1 mole. Then we're going to go from moles of hydrogen gas to moles of hydrogen chloride using our molar ratio. So we have a 1 mole of H2 to 2 moles of HCl. Okay, we're going to use that ratio. Then we're going to go from moles of HCl to liters of HCl using that 22.4. There's 22.4 liters in 1 mole. Okay, so that is our map. So we're doing 3 conversions, so draw 3 lines. Starting off with 5.33 times 10 to the 23rd molecules of hydrogen gas. Okay, so we have molecules on top. So molecules goes on the bottom, and Avogadro's number is going to go with it. 1 mole of H2 will go on top. Okay, now we have moles of H2 on top, so we're going to put moles of H2 on bottom, and this is when we're going to use our molar ratio. So 1 mole of H2 goes on the bottom, 2 moles of HCl is going to go on top. Last conversion, we're converting to liters. So we're going to have 1 mole of HCl on bottom, 22.4 liters of HCl on top. Now remember, this 22.4 can only be used with gases. That's why it's important that it says hydrogen chloride gas. So we're going to have 5.33 times 10 to the 23rd times 2 times 22.4. That's going to give us 2.39 times 10 to the 25th on top. And then we're going to have divide by Avogadro's number on the bottom. 23. And that's going to give us 39.7 liters of hydrogen, not hydrogen, sorry, hydrogen chloride gas. Okay? So that's how we convert using 22.4. So now we're going to talk about calculating using calculating the volume of a liquid using density. So that was volume of gas. Now we're using density, okay, for liquids. So for liquids, we cannot use 22.4 liters equals 1 mole conversion, as we aren't dealing with a gas. But do not worry, you'll be giving another piece, density, which you can use as a conversion. Think of density as number of grams per milliliter as being like an equality of number of grams equals 1 milliliter. Okay, it's a conversion factor. So this is a conversion factor. So I'm going to give you an example of density. Water's density is 1 gram per milliliter. And so what that means is if I have 1 gram of water, liquid water, its volume will be 1 milliliter. And vice versa. If I have 1 milliliter of water and I go over and weigh it in my lab, it's going to weigh 1 gram. So we can use that to convert between grams and milliliters and grams. Okay? So here is a conversion. So we're going to use molar mass convert from moles to grams. And then we'll use the density to convert from grams to milliliters, using it like a conversion factor. So our first example says, how many liters of liquid bromine are needed to react completely with 400 grams of calcium iodide? Okay, the density of liquid bromine is 3.12 grams per milliliter. Okay, so it's liquid bromine is reacting with calcium iodide. So we're going to put bromine is a liquid. Okay, bromine is a liquid. If you look on the periodic table, it's blue. Plus calcium iodide is going to produce iodine, which is a solid, if you look on the periodic table, and calcium bromide. Okay? Now, forgot, bromine's also diatomic. Okay? So, when we write these, if we try to balance, we actually see that we are going to have ones all in front because we got 2 bromines on both sides, 2 iodines on both sides, 2 calciums on both sides. Okay? So now we're going to do our conversion. So again, we are given 400 grams of calcium iodide, and we need liters of bromine. Okay, this is liquid bromine. So we're starting with grams, 400 grams of calcium iodide. We're going to convert grams of calcium iodide to moles of calcium iodide using the molar mass of calcium iodide. Then we're going to convert calcium iodide, moles of calcium iodide, to moles of bromine using our coefficients. It's a 1-to-1. 1 mole of bromine to 1 mole of calcium iodide. Okay. And then we're going to convert moles of bromine to grams of bromine using the molar mass. And now this is Br2 of Br2. Then we're going to convert grams of bromine to milliliters of bromine using the density of bromine, which is 3.12 grams per milliliter. Then we're going to convert milliliters of bromine to liters of bromine. Using the conversion, there's 1,000 milliliters and 1 liter. So that's a lot of conversions. We're doing 1, 2, 3, 4, 5 conversions. Okay? So let's set this up. Draw my line. Woo. A long line. 1, 2, 3, 4, 5. Have it extended a little bit. Okay? So we're starting with 400 grams of calcium iodide. Okay? So on the bottom is going to be grams of calcium iodide. So we got to calculate the molar mass. I'm going to go over here. Calculate the molar mass of calcium iodide. Calcium's mass is 40.08 plus 2 times iodine's, which is 126.91. So 40.08 plus 2 times 126.91. So that will give me a mass of 293.90 grams per mole. So I'm going to have 293.90. I'm going to have to squeeze it in there. Grams of calcium iodide in 1 mole of calcium iodide. Okay. Then I'm going to convert moles of calcium iodide to moles of bromine. Okay, so using our mole to mole ratio, 1 mole calcium iodide to 1 mole of bromine. Okay, so that will get us to moles of bromine. Now I'm going to convert moles of bromine to grams of bromine using the molar mass of bromine. So 1 mole of Br2. Grams of Br2 is going to go on top, and so we got to calculate that. Br2 it's going to be 2 times 79.90. So 79.90 times 2. It's going to give me 159.80 grams per mole. So 159.80 grams of bromine. Then my next conversion, I'm going from grams of bromine to milliliters of bromine using my density. So remember what this means is that there are 3.12 grams in 1 milliliter, or 1 milliliter weighs 3.12 grams. Excuse me. And so I have grams of bromine on top, so grams of bromine is going to go on bottom, and it's going to be that 3.12. And then 1 milliliter will go on top, and that's 1 milliliter of bromine. So that gets me to milliliters of bromine. Then I need to convert to liters, because it's asking for liters, using 1,000. So we got 1,000 milliliters of bromine in 1 liter of bromine. Now, do y'all understand, or do y'all now understand why we make you do dimensional analysis? Because look at how many conversions we're having to do. If you did this all over the place, guaranteed you're going to get something wrong. Okay, it's easy to make careless mistakes if you keep doing all these conversions in separate places. You want it all in one place, all nice and neat. There's enough room for you to do it. So multiply the top, 400 times 159.80. Okay, so 400 times 159.80. And that's going to give me 63,920 on top. Then you're going to have 293.90 times 3.12 times 1,000. So that's 916,968. So then you're going to divide 63,920 divided by 968. That's going to give me 0.06971. 4 sig figs. That is liters of bromine. Okay, so that's So what that is that, to put that into perspective, that is 69 milliliters. Okay, so you get 69 milliliters, but it asks for liters. Now the next one, it says how many liters of hydrogen gas at STP are required to react with 40 milliliters of liquid bromine. So now we're actually starting with the liquid in the synthesis of hydrogen bromide gas. Okay, so we're making hydrogen bromide gas. So we're going to have hydrogen gas, H2 gas, plus Br2 liquid yields hydrogen bromide, and that's a gas. Okay, so when we balance this reaction, we're going to put a 2 in front of HBr, and there's going to be 1s here. Okay, so start with your given. We are given, in this case, we have it already in milliliters. We're given 40 milliliters of bromine, and we need liters of hydrogen. So we're going to be using both of our conversions we learned today. So we're starting with 40 milliliters of bromine. Now this is liquid. So we're going to convert milliliters to grams of bromine using the density, that 3.12 grams per milliliter. Okay? Then we're going to convert grams of bromine to moles of bromine using the molar mass of Br2, which thankfully we've already calculated that. Then we're going to go from moles of bromine to moles of hydrogen using the molar ratio. So 1 mole of bromine to 1 mole of hydrogen. Okay. Then we're going to go from moles of hydrogen to liters of hydrogen, not using density because this is a gas. We're going to use 22.4 liters equals 1 mole. Okay, so let's set up our conversion. We got 1, 2, 3, 4 conversions. So I'm going to draw 1, 2, 3, 4 lines. Extend that. So starting with 40.0 milliliters of bromine. First, we're going to use our density. So, in 1 milliliter of bromine, it's going to weigh 3.12 grams. You'll have 3.12 grams of bromine. Okay? So, notice we used it set opposite way here than we did here. Then, we're going to go from grams of bromine to moles of bromine using the molar mass of Br2, which we calculated up here. That molar mass is 159.80. Okay, so we got 159.80 grams of bromine is in 1 mole of bromine. Then we're going to use our mole to mole ratio from our balanced equation. So 1 mole of bromine to 1 mole of hydrogen. Okay, because that's from our balanced equation. So we're here. Now we're going to go from moles of hydrogen to liters of hydrogen using 22.4 liters. So 1 mole H2 is 22.4 liters of H2. So we're going to do 40 times 3.12 times 22.4. That'll give us 2,795.52 on top. And then we're going to have 159.80 on the bottom. So that's divided by 159.8. That will give us 17.49 liters of H2 gas. Okay, so 17.49 liters of H2 gas. So that's converting using density. So if we have the volume of liquid, we can use density. If we have the volume of gas, we use 22.4. Now, the last thing we're going to talk about today is calculating percent yield. Okay? So, in a perfect world, we will make 100% of the theoretical yield. Now remember, the theoretical yield was calculated using stoichiometry. Okay, that is how much we theoretically can produce. Okay. Now the experimental yield is what you actually made. So you went into the lab, you did this reaction, and it's what you actually produced. Okay. Now the percent yield is what percentage of my theoretical did I actually get. So it says not always will you actually make what were you supposed to. Okay. The percent yield is the comparison of what you got versus what you're supposed to get. So sometimes it's called the percent efficacy or efficiency. Okay. So here's how we calculate it. So it says in our first example, it says that if 32 grams of methane are burned in a combustion reaction and 30 grams of water are experimentally produced, what is the percent yield of the reaction? Okay. So first, we need to figure out, so it's given us, it said that 30 grams of water was produced in the lab. We're given 32 grams of methane. So we need to figure out how much water, how many grams of water is produced if I combust, or how many grams of water can be produced if I combust 32 grams of methane. So we're going to write methane, it's a gas, plus O2, gas, gives us CO2 plus H2O. Okay? So when we balance this, we're going to have a 2 here. So that is 2 plus 2 is 4. We're going to have a 2 here. So 1, 2, 1, 2. Double check. 1 carbon, 1 carbon. 4 hydrogens, 4 hydrogens, 4 oxygens. 2 plus 2 is 4. Okay. So now we are going to calculate. We're trying to see how many grams of hydrogen can be produced if I'm given 32 grams of methane. So I got 32 grams of methane. Okay, so we're going to convert grams of methane to moles of methane using the molar mass of methane. Then I'm going to convert moles of methane to moles of water using that mole-to-mole ratio. 1 mole of methane to 2 moles of water. Okay, then I'm going to convert moles of water to grams of water using the molar mass of water, which is 18.02. Okay, that's something that honestly we use water as molar mass all the time. So now, so what we're trying to find is we're trying to find the theoretical yield. Okay, we're trying to find the theoretical yields, and then what we'll do is we'll plug it into this formula. Our experimental yield was given. It said that 30 grams of water are experimentally produced. So this is the experimental yield. So we'll take the experimental yield, divide by the theoretical that we calculated, and get the percent yield. So let's calculate that theoretical yield. So we're starting with 32 grams of methane. So we're going to put grams of methane on the bottom. Let's calculate that molar mass real quick. So we got 12.01 plus 4 times 1.01, and we should get 16.05. Okay, so we got 16.05 grams of CH4. That's 1 mole of CH4 on top. Okay. Then we do a mole-to-mole ratio using our coefficients. So 1 mole of CH4 on the bottom, 2 moles of water on the top. Then we're going to go from moles of water to grams of water using our molar mass of water. So 1 mole of water is 18.02 grams of water. So this is going to give us our theoretical yield. So 32 times 2 times 18.02. That gives me 1153.28 on the top, divided by 16.05. That's going to give me 71.86 grams of water. Okay? So that's how much water we can produce if we have 32 grams of methane. Now, they said the experimental yield was 30 grams of water. So to find the percent yield, we take our experimental, which was given, divided by the theoretical, multiply it by 100%, or 100, and then you'll end up with a percentage. So 30 divided by 71.86 times 100, that's going to give me a 41.75% yield. That is not a good percent yield. Okay, you didn't even get half of what you needed, so something went wrong there. Now let's look at the next one. It says the reaction of combustion of octane, okay, so octane C8H18 in an engine is known to be only 74.3% efficient. How many grams of water would you experimentally expect to form if 90 grams of liquid octane are burned? Okay, so for this one, you're going to have to kind of do it kind of backwards. So we first need to write our balance equation, C8H18, okay, plus O2 is going to yield CO2 plus H2O, okay? So first we need to balance. There's going to be 2 there, and then there's going to be an 18 here. So that means that's going to be 16 here. Oh wait, sorry, hold on. 18 times 2 gives me 36 here, right? No, that's 18. Wow. Okay. Then 25 here. Is that right? 2, 25, 16, 18, 16, 36, 50, 16 times 2, plus 18. Yeah, okay. So now what we're trying to do is asking us how much water would you experimentally expect. Well, we know that it's 74.3% efficient, okay? So what we're going to do is we are going to calculate the theoretical yield of 90 grams of liquid octane were burned. We're going to calculate that theoretical yield of water, and then what we'll do is multiply it by because remember 0.743 to get our experimental yield. Okay, so we're going to start with 90 grams. Oh, it said liquid. Wow. Okay, 90 grams of octane. Okay, we're going to convert grams of octane to moles of octane using the molar mass of octane. Then we're going to go from moles of octane to moles of water using those molar ratios. So 2 moles of octane to 18 moles of water. Okay. Then moles of water, 2 grams of water using the molar mass of water. And then after we get this answer, we're going to multiply that by 0.743. That should give us our experimental yield. Okay. So, let's calculate. Do 1, 2, 3. So we got 90.00 grams of octane. Okay, so grams of octane is going to go on the bottom. We need to calculate that molar mass. So 8 times 12.01 plus 18 times 1.01. Let's calculate that. 8 times 12.01 plus 18 times 1.01. It's going to give me 114.26 grams per mole. Okay, so 114.26 grams of octane and 1 mole of octane. Okay, and then we're going to do our mole to mole ratio. 2 moles of octane to 18 moles of water. And then we're going to go from moles of water to grams of water. 1 mole of water using our molar mass of water, 18.02. So this should give us our theoretical yield, 90 times 18 times 18.02 on top. It's going to give me 29,192.4. And then 2 times 114.26. It's going to be 228.52. So I'm going to divide those. 29192.4 divided by 228.52. That's going to give me 127.6 grams of water. Theoretically, that's how much I can produce. But we know that's not how much I do produce because it's only 74.3% efficient. So I'm going to take that theoretical yield, this is the theoretical yield, multiply it by 0.743, and that will give me my experimental yield. So 743, that's going to give me 94.91 grams of water. That's experimentally, that's how many grams of water is produced when your combustion engine runs. Okay? So, that's it for today. If y'all have any questions, just please make sure you're coming by tutorials.